through porosity calculations okay in the homework. And what I'd like to do today is I'd like to start off with a little bit of a review from what we covered last time, where we really started to talk about the structure of what's happening inside of the system. You'll remember that we pointed out that concrete, much like our good friend SpongeBob here, is a porous material, just like a sponge. There are holes or there are openings inside of the structure of the system that's going to allow gas and liquid to go into the system. Now this is going to be important when we start to talk about things like durability concepts, when we start to talk about chlorides going into the system. Chloride ions will be transported through the fluid, or when we start to talk about drying where water is leaving the overall system. Right? The other things that we really started to talk about last class, in addition to the overall fact that concrete was a porous material, is we said that it really depends upon the scale at which we're looking at the concrete on. So we said that the scales could be broken up into basically three types of length scales. Right? The first one that we talked about was really the macro length scale. And here we're really talking about seeing things on a meter or foot-long size scale. So essentially this is the type of size scale when you step back and you look at a bridge or you look at a building. And the main distinction that we're going to make here is that the overall concrete is basically going to look very homogeneous. Now this is important because this enables us, when we start using calculations, we can start to say that the concrete has a single property. So the concrete will have a single strength, or the concrete will have a single value of elastic modulus. And we can treat this very complicated material with a very simple property that sort of averages out all of the other features. The second length scale that we're going to talk about is the meso-length scale. And here when we talk about the meso-length scale, what we're really talking about is we're talking about things on the centimeter or millimeter or inch size scale. This is essentially going to be the scale that we look at if we were to slice a piece of concrete open and we were going to look inside. And what we can see with our with our naked eye is we can see that the concrete is going to be a two-phase or a three-phase system. When we're talking about a two-phase system, we're mainly talking here about those two phases being the aggregate and the paste. Now here we're going to assume that the aggregate is one uniform part of the overall system. The paste is a uniform, another phase that's completely homogeneous. And if we want to add in a third phase, we'll basically say that this is the interfacial transition zone, or ITZ, that surrounds each one of the aggregate particles. All right? So these are the three phases that we're going to look at, and the big power that comes in here is we can start to say that the engineering properties that we need for the macro scale are simply going to be a function of the properties of the individual constituents, the aggregate, the paste, and the volumes of those materials. All right, and this starts to give us some great power. So we can start to look at things on the scales where we start combining those materials. If we take a step even further down in size, we would get down to the micro scale. And the micro scale is typically, we're going to be looking at things in terms of microns. And just to give you a little bit of a reminder, the human hair is about 75 microns wide. All right, so if you try to think of things in terms of that scale, you'll remember that the human hair is about 75 microns wide, and we're looking at things that are much, much smaller than this. In this particular model, this particular length scale, we'll be looking at things like porosity. All right, we'll be looking at things like our calcium silicate hydrate, calcium hydroxide, unhydrated cement particles. All right, so we're really looking at what's taking place on the finer scale. The next thing that I'd like to review is we started to talk a little bit about some of the different types of models that we saw for porosity prediction, or that gave us a little bit of an idea of what this porosity actually meant. The first model that we looked at was really the dollar bill model, and what we're trying to get an idea of is how water to cement ratio is related to porosity. So what we asked you to assume here was, we said, let's take the dollar bill and we will add in particles that are either cement pennies or actual pennies, All right, and we're going to say that that is the cement part of the system, and the part of the dollar bill that's still exposed is the overall water that's in the system, or the porosity. And what we saw is that the water to cement ratio is going to be the single most fundamental property that is going to be related to porosity. The basic relationship is the higher the water to cement ratio, the greater the porosity. Right, so this was the basic idea that we looked at when we started to talk about the dollar bill model. Right, when we took this a step further, all right, we started to get into some simple reaction models, and this is what the homework was based on, where you had a single volume of water, and that volume would be reacting with a volume of cement, and it gave us a conceptual illustration of the fact that if the water to cement ratio is too high, we have leftover water, and that leftover water goes on in the system to make the capillary porosity, all right, which are the big pores that we have in the overall system. We then said we could take this and we could start to refine this, and we could use things like Powers' model. And Powers' model starts to allow us to refine these concepts a little bit and starts to give us better calculations on the volumes of the pores that are being calculated, and Powers goes as far as to separate these pores into big pores, which he refers to as capillary pores, and small pores, which he starts to refer to as gel pores, which are part of the overall structure. We said the fourth type of model that we were looking at was really the NIST models, which are the new computer simulation type models, which give us a much greater capacity than any of these three models. And the big thing here is we can not only calculate the volume of the materials, right, but now we can start to look at the volume of the individual components. So no longer are we basically assuming that everything is a calcium silicate that's reacting to form a calcium silicate hydrate. Now all of a sudden we can see the reaction that's taking place of each of the individual phases. All right. In addition, we can start to get an indication of the spatial distribution of some of these phases, which really gives us some great power as we start to move forward. All right, so we can start to get an idea of what the pore space is, what the total volume of that pore space is, but we can also start to see how that is distributed throughout the system. And what we'll actually see as we go through some of the remaining lectures is the distribution of this porosity is also very, very important. Right? Before we get on and we go into more of the analytical side, where we start to go into some more of the calculations, what we'd really like to do is take a little bit of time today and look in at the pore structure of our concrete, and really look at the pore structure and really what is and what's not there. All right. So what we want to do is we want to look inside the structure of cement paste, and we want to get an indication of what these pastes actually look like. We want to look at real microstructures. So what I'll actually do is I'll spend a little bit of time. Last lecture we went through the microstructures very quickly. This lecture, what I'd like to try to do is I'd like to try to focus in a little bit more on what the water to cement ratio, what the impact of that actually is. The second thing I'd like to really do is look at what happens as the system ages, or as the system hydrates, as we get to higher and higher degrees of hydration. The next main point that I want to try to make is I'm going to break this up, and I'm going to talk a little bit about some of the problems that we have in measuring porosity. You may say, if porosity is so important and porosity is the main issue, why don't we just measure porosity and forget all about this water to cement ratio thing? And what I'm going to do is I'm going to talk about the fact that this is not done because it's hard to do. All right, and we'll talk about some of the complexities that lead to this as we go through. So the measurement of porosity is a very, very hard, challenging problem that people are still focused on today. We'll look at some of the individual components. So we'll look at some of the unhydrated cement. We'll look at the calcium silicate hydrate that's reacted. We'll look at the calcium hydroxide. And then we'll look at some of the debate that exists around the interfacial transition zone, or the ITZ. So to start off, we'll talk a little bit about the pore structure, and this will really build on the last lecture, and we'll start to talk a little bit more about conceptually what is and what isn't in the overall system. Right, you'll remember that we talked about Powers' conceptual model. And in Powers' conceptual model here, there were really two different types of porosities that were identified. All right, Powers basically said that there were going to be two types of porosities. There were going to be these large voids that were forming, these capillary voids, and there were going to be the smaller voids that were forming inside of the hydrated product. The larger voids he referred to as capillary voids. The smaller voids that were in the hydrated product he referred to as gel porosity or gel voids. Now he made this assumption based on the fact that the particles would be spherical, and he really sort of dreamed this up based on some different ways that he had of probing the microstructure. You'll remember that I mentioned that this is not a micrograph, this is not a direct picture of the system. This is simply a conceptual illustration of what Powers approximated the system or thought the system probably looked like. Right? What we will find out is that to some extent the properties of concrete are going to be influenced almost as much by what's not there as what is there. Much like our Swiss cheese that we see in this picture to the right, the holes in the Swiss cheese, are an important component of the Swiss cheese. The holes inside of concrete are really the key issue. Porosity is the main key issue, and the one thing that I will say, people will go through great ends to really look at this. He or she who controls the porosity really wins the game. Almost everything that we're going to look at, as we start to go through the rest of the semester, as we start to look at new innovations, as we start to look at things that are really revolutionizing the systems of concrete, are really going on in this phase here. They're really all measures that are focused on how do we control the porosity of the system. So when we talk about things like water-reducing admixtures, it's an attempt to control the porosity of the system. When we talk about air entrainers, it's an attempt to control the porosity of the system. When we talk about silica fume, it's an attempt to control the porosity of the system. So again, the main key goal, if we take a step back and we look at Powers' conceptual model, the real step forward that we've taken over the last 40 to 50 years is really trying to control the structure of this material, and our idea is really to try to minimize these big capillary particles, or these big capillary pores. The gel pores are fixed. The gel pores are part of the hydration process, so they're fixed in the overall system. What we want to do is try to reduce the porosity, and we want to reduce these large capillary pores that are in the overall system. He or she who controls the porosity are really going to win the game, and that's really what we're going to be after in almost every single one of the remaining lectures that we're going to be talking about. Inherent in that is controlling the porosity and controlling the water to cement ratio. The next step that I want to do is I really want to look at some of the conceptual ideas, inside of a microstructure. Now, I'm not going to look at the simple models that we talked about last time. What I'm going to do is I'm going to actually look at real micrographs here and try to demonstrate some of the same types of concepts that will hopefully create a little bit of a link between some of the mathematical modeling that we're doing and some of the pictures that we'll actually see that most of the people are going to look at when we look at the structure inside of a cement paste. So if we take a step forward, we can see a cement paste that looks like the image that we've got shown here on the screen. And what I will point out, and I didn't mention this a lot in the last lecture, but this is not an optical microscope image. This is a scanning electron microscope image. So what we're actually looking at here, the colors represent a density inside of the material. The lighter the color, the more dense the material is. The darker the color, the less dense the material is, getting up to a point where you can see very, very dark regions. Those dark regions like the one that I've just circled right here. This dark region is essentially a pore, an empty space inside of the overall system. So we have these dark regions which are empty spaces. We have very, very light regions like we can see on the other side of the diagram, which I've drawn an arrow to here. This very, very light region is a very dense region, and this region over here is going to be our unhydrated cement particle. This is cement, the dry gray powder that was put into the system that we're waiting to react with the overall water. And what you will see is that this image has a series of gray levels that go somewhere between the black porosity that we see over here, which was the open pore space, which we see on the left-hand side, and the white unhydrated cement particle that we see on the right-hand side. We'll see the aggregates will be sort of this uniform gray color, and these will be fine cement powders. All right, our fine aggregate powders, fine aggregates, not cement powders. These are fine aggregates, sand in the overall system. And then you will look at the fact that these sand particles, so we've got an aggregate here, we've got a second aggregate, a third aggregate, a fourth aggregate. In between these aggregate islands, what we will see is a glue that is holding the overall system together. This glue that's holding the overall system together is that mixture of the dried cement powder and water. And what you will see is that there will be a few things that are pretty interesting about this glue. You will see that there is a very dense region, which is highlighted here by the aqua type arrow, where you will see that it is a darker grayish color. This is a very dense region of the paste. You will also see that the yellow arrow points to the same type of material, the same calcium silicate hydrate in the overall system, but it's much more porous. So it's a porous region of the paste, a lot of more openings, and here you'll see things that are much more like our capillary porosity than what we saw in the dense region. You'll also see a region that is a light grayish color, and that light grayish color happens to not be our calcium silicate hydrate here. This is our calcium hydroxide that's forming. And one of the things that's interesting to note here is our calcium hydroxide is going to be forming mostly on the surfaces of particles, so you'll see it forming predominantly or preferentially on the surfaces of aggregates. So as the calcium hydroxide begins to come out of the solution, you will see that it will start at a surface, and you'll see a lot of the surfaces will tend to have calcium hydroxide on them. You'll also see regions where water may have been moving through the system when the structure hardened, when the concrete set, and these are typically referred to as bleed channels. But the main thing that we want to look at as we go through here, all right, is just getting a little bit of a bearing on what a real microstructure looks like. We've got our aggregates, which are numbered here 1, 2, 3, and 4. We've got our dense region of hydrated paste. We've got a more porous region of that overall paste as well. Right? If we take a little bit of a step further into this micrograph, all right, we can start to see some of these regions identified a little bit more clearly. You can see up toward the top of the graph, we've got our unhydrated cement particle. Again, this is that gray powder, very, very dense material that is yet to react with water on the inside. The outer surface of that particle has been reacting, but the inner portion of that is a white island in here, and that white island is essentially unreacted cement powder in the overall system. Slightly below that, you can see a dark region, and those dark regions are going to be pores, typically going to be entrapped air or capillary pores, depending upon the size that we're looking at. And then what you will see is these two different types of glue that we were talking about. Typically around the edges of the cement particles, you will see a very, very dense gray matter, and that dense gray matter is the calcium silicate hydrate that's forming at the surface of the cement grain. You will also see some of the more mushy gray matter, or the open space, and that is a low density calcium silicate hydrate that's forming in between the particles. All right, so what are some of the things that we can start to look at when we start to look at these systems? Well, one of the things that we can look at is the effect of the water to cement ratio. So on our left-hand side, we have a water to cement ratio that's a 0.45. On our right-hand side, we have a water to cement ratio that's a 0.3. And what I'm going to do on the next two slides is I'm going to look at the 0.45 in a little bit more detail, and then I'm going to shift over to the 0.3 paste. When we look at the 0.45 water to cement ratio paste, we see a lot of the features that we were talking about before. We see our unhydrated cement particle that's shown here. We see our porosity. And again, we see sort of the two types of structure. We see sort of this open calcium silicate hydrate, or low density calcium silicate hydrate, and then we start to see a higher density that's forming around the ridge of our cement particles. This is in a higher water to cement ratio system. What I'd like you to do is compare and contrast this to the next image that you'll see, which is our 0.3 water to cement ratio system. And what you can see here is, while we still have our unhydrated cement particles, you'll see that the area between these particles is much more uniformly dense. And this can make sense to us. This is exactly what we would expect to see. As the water to cement ratio decreased, we would expect to see the porosity decreases. decreasing. As the porosity decreases, that dark area, that open space tends to start to go away, and we start to get a much more solid overall system. So again, here's our 0.3 water to cement ratio system, much more uniformly gray, uniformly solid. When we look at the 0.45 water to cement ratio system, you will see that there are some dark regions that are uniformly gray, but there are other regions where we tend to have more porosity. And this is going to be one of the biggest distinctions that's made between the two different water to cement ratios. Okay. We can take this a step further, and we can look at some of the types of how some of the properties are going to be influenced. So here what we've plotted along the x-axis is the solid to space ratio. So if we actually look at the solid to space ratio of 1, which is down in this corner, this is a solid to space ratio of 1. This is almost entirely hydrated cement particles. On our y-axis, we've got compressive strength of the overall cement paste, and on our x-axis, we basically have increasing water to cement ratio as we move toward the right of the system. So as we increase the water to cement ratio, we are going to increase the porosity in the overall system. We're going to basically start to see a decrease in compressive strength. All right, this is much like what we talked about last time. As the system becomes more porous, the strength is going to be lower. As we start to reduce the overall pores in the system, the strength is going to tend to trend upward. Now, I've shown conceptually two small diagrams toward the bottom. We can see a low porosity paste with very few pores. On the right-hand side, we can see a high porosity paste. And not surprising, we would expect the higher porosity paste to be less dense and have a lower strength than what we would see in the low porosity paste. We can also take this a step further and not just look at strength. We can start to look at the path that it would take something to flow through the system, or the permeability of the overall system. And what we can see is when the permeability is low, whatever is flowing through the system would have to travel through the relatively solid material, and then it can accelerate as it goes through the pore spaces, but it's going to take a lot longer time or a longer path to go through those solid materials than if we had the system that we saw on the right side, which is much more porous, where whatever's traveling through the system can go through the open pores and get through to the other side very quickly. Now this could be almost anything that's traveling through the system. All right, we can consider this to be water. All right, we can consider this to be small children, whatever might be moving through the overall system. All right. If we're looking at water, we could measure this as a permeability coefficient. And what we can see is when the system is very porous, the permeability coefficient, which is shown as our second y-axis, tends to be very high. As we decrease our water to cement ratio, we will find that permeability coefficient dropping off significantly. And what we will find is that permeability coefficient will make a huge change once we get to this region where we've got this solid yellow line that I've been filling in, and that's a water to cement ratio that's about 0.4 or 0.42. So all of a sudden we start to tie this back in with a little bit of what was seen in some of the previous slides, that 0.42 starts to tend to be magical water to cement ratio. Once we get below that, the permeability coefficient drops off significantly because we start getting rid of the capillary porosity. We start getting rid of a system that looks like what we've got on the right, which are large pores that are heavily connected, and it starts to become much more difficult for things to flow through the system. The other effect that we can start to see is we can start to see the effect of continued hydration, or the effect of aging, as we go through and we look at the microstructures. So here we have a system at 3 days old. This is just a typical cement paste that's been mixed. Again, you can see the aggregate particle. You can see we've got a scale bar that's about 40 microns. Again, that's about half the size of the human hair. And what you can see is there are going to be these whitish spots, which are going to be our unhydrated cement paste. We've got our darker gray spots, which are going to be our calcium silicate hydrate. We've got some calcium hydroxide that's thrown in the mix. This is our free lime. But you will notice that a lot of the background tends to be open, tends to have a lot of porosity. As the system continues to hydrate, what we're going to see is that this unhydrated cement particles, these particles are going to start to reduce in their size because we're consuming up that unhydrated cement in part of the reaction. It's going to be reacting with the water in the system, and what we are going to see is that the system is going to start to become more dense. So as we shift forward and we go from a 3-day system to a system that's 100 days old, we still have the aggregate. What you will notice is that a lot of our bright white particles, like this one here, are unhydrated cement particles. We see a lot fewer of those around. They're taking up a lot less surface area. And what we start to see is that this cement paste has started to fill in substantially. So the main thing that we can take away from this is as we go from a 3-day system and the system continues to hydrate, let's say out to 100 days, the system begins to densify, hydration continues to proceed, and the porosity starts to fill in. And this starts to explain why we start to see better performance in the concrete after we allow the concrete to sit for a little while. At 1 day we may have a low strength, or at 3 days we may have a low strength, and that's because we have a substantial amount of porosity in the system at 3 days. However, if we shift to 100 days, we notice that that porosity begins to go away, the system begins to become more dense, and as a result, the system will be stronger. We'll also see that the transport properties will change as we go as a function of time as well, and it will be harder and harder to transport fluids, or gases through the system as it hydrates more because it begins to disconnect the porosity and begins to fill in some of the porosity. So the main thing to take away from this is at early ages, the paste tends to be much more open. We have much more unhydrated cement. And we can see a lot of open paste around the aggregate. At 100 days, we can see that much more of the hydration has taken place, and we've started to really fill in the overall system. One of the questions that you may be asking, though, is where do these pores originate, or where do these pores come from? And what I've done here is I've taken a picture that was taken immediately after mixing. So this is an image that was taken immediately after mixing, and what I've done is if you go to the original article, you will notice that this picture doesn't necessarily look like this. What I've done is I've reversed the colors from what they've shown so that the colors match up with everything else that you're seeing with the scanning electron microscope images. So again, the cement particles are going to be shown here as our light color in this particular image, and our dark spaces here are going to be the overall water. What you will see is that the pores that we will see at later ages are essentially leftover space that initially started in the fresh concrete or the fresh paste system that was between the cement particles. This is the space that was initially filled in with water. So at early ages, you can see that there's a substantial amount of water in the system, and that water is essentially separating these cement particles. As the system hydrates, that water begins to be consumed, that water is used up, and all of a sudden we'll see this water space begin to start filling in with hydrated products. And that pore space is essentially going to be what's left over, or the space in between those particles where the hydration product doesn't fill in. So this is really the origin of some of these pores. So that gives us a little bit of a look inside what these pores actually look like, gives us a little bit of an idea of what's happening when we start to look at variations in the water to cement ratio. Again, as the water to cement ratio increases, as we see the water to cement ratio go up, the porosity of the overall system increases. As the system hydrates more, or as the system gets older, the porosity is going to decrease because the hydration products are filling in that pore space. The next thing that I want to talk about is how we measure this porosity. And I'll talk a little bit about some of the problems that are associated with measuring the porosity. As I mentioned earlier, you may say, well, if porosity is so important, why don't we just measure porosity and forget about measuring everything else? And the real answer there is it's hard to measure the porosity, and it's hard to get a really good, accurate measurement. And one of the reasons for this, we can actually think about in a very simple conceptual type of illustration here. And this is an illustrative concept that I've borrowed from Tom Mason, Mason. And basically the idea here is you'd be asked to describe what's happening behind this dark black screen simply by sticking your hands around that screen. And many times this is what we're doing with some of the different techniques that we're trying to use to probe the system to get an idea of what some of the measurements are. So you might stick your hand around the screen and you might say, well, I feel something that's leathery and feels a little bit like a cylinder. Somebody else may stick their hands around the screen and say, well, I feel an object that feels really smooth and feels fairly thin. Somebody else may say, I feel something that feels, feels large, massive, And you say, well, how did everybody stick their hands around the screen and feel something different? Well, it depends on what the object was that's behind the screen. All right? The person who was feeling something leathery may be feeling something like this image that we see on the right on the top. The person who's feeling something that's smooth and thin may be seeing something like this image that's shown in the middle. And someone who's seeing something that's large and massive may be feeling something like the image that's shown on the bottom. And all of these people are feeling the exact same thing, but they're feeling it at a different point, and they're typically going to be feeling it with a little bit of a different touch or a little bit different scale. And what you can see is that each one of them has basically been describing what happens when they touch the elephant, what they got out of probing the elephant. So someone here said that it felt like a cylinder, and they were probably touching the trunk. Somebody said that it felt really smooth, and they were probably touching one of the tusks. And somebody else said that it felt, large, massive. Maybe they were touching the body of the elephant. Now, each one of these people is touching the elephant and trying to describe the elephant based on what they're touching, but it depends on where they're actually probing the system. And this is the same type of thing that we're looking at when we start to talk about probing the system of cement paste. When we start to measure, it's really a question of how close we look at the system. If we look at the macroscopic view, right, the system we said was homogeneous. If we start to look at the mesoscale, we start to see that we have our aggregate particles that are going to be separated by our paste phase, right? If we look a little bit closer, we're going to see pores, and if we get even closer and closer, we're going to start to see different scaled items. So the length scale that we're looking at really makes a distinction between what we're seeing in the overall system. And the biggest problem that we're dealing with in cement paste is we are covering 7 or 8 orders of magnitude when we are trying to describe the pores. We're talking about something that is enormous, something that's the size of an entrapped air void that may be something like centimeters or millimeters, all the way down to interparticle space or calcium hydroxide crystals, down to interparticle spacing, which may be on the nanometer scale. And what we're trying to do is we're trying to come up with a technique that tells us about all of these pores. And that's a very difficult thing to do. What we're going to see is that most of the techniques that are out there can really only work in a very narrow range. They may work in pore sizes of 1 or 2 orders of magnitude, but to cover this massive scale, right, these 8 or 9 orders of magnitude that we need to deal with, is a very, very difficult thing to ask one particular simulation model or one particular experimental technique to do. The simplest approach that most people commonly use is something like microscopy. Now, if we look at the top of this image, you can see that the least magnification that we would have is something that's really at a visual level. We may be looking at it just with our eyes, or we may be looking at it with a little bit of magnification. But essentially, what we're going to be able to see there are the types of things that we saw in the previous pages. We'll see some coarse aggregate. We'll see that it's being connected with paste, but that's really all that we can see. Maybe we can see some air voids, but we're really looking at this with a very simple type of magnifying glass or just with our unaided eye. If we go to a petrographic microscope, we're looking at the next scale down. We may be looking at a 25 or 250 times magnification level. And what we can start to really make out are some of the finer aggregates, some of the air voids, looking at some of the cracks that are in the system. But we're really looking just at the next length scale down. down. So it was the same system, but we're starting to see different features. If we go even further, we can start to look at the SEM, which can start to give us the idea of how the cement particles and the sand are going to be juxtaposed. All right. If we go even finer, we can start to see the individual particles and start to get aspects of the porosity. And most recently, if we start to look at the nanoscale, we can start to look at things like atomic force microscopes. And those atomic force microscopes can really start to tell us about how the structure of the overall system is really made up. But what you can see here is, again, this level of complexity that depending upon the level of magnification that we use, you would get a very different image of what that overall system looks like. An alternative technique that people have used is mercury intrusion porosimetry. Now, mercury intrusion porosimetry is a fairly straightforward technique. What I'm going to do is I'm going to hit some of the high points here. What I would like to point out is that while people use it and it has a place, it's really not the be-all, end-all of all the microscopy measurements, or all the porosity measurements, and I'll try to explain a little bit of why that is. Right, what we'll do is we'll actually start off with a container, which we see on our left-hand side of our screen, and that's a large open container, and inside of that container we have a cement paste that contains pores. So we've got our cement paste, which is shown here in gray, we've got our pores that are shown here in white, and we've got the container that's basically outlined by the light-framed box. And what we're going to do is we're going to start to fill that container with a non-wetting fluid, something like mercury. All right, mercury intrusion porosimetry. And the idea here is that mercury is only going to go into the pores, all right, that correspond with a particular pressure. So the basic idea here is that if we use a relatively low pressure, we can push the mercury into just the large pores. And if we look at this, we can keep track of this on a diagram that's shown on the right-hand side. We can look at, on our y-axis, we've got the volume of pores that are being filled up with mercury, so we can track the volume of mercury that's going into the system. On our x-axis, we can basically keep track of the pressure that we're pushing on the system, and that pressure can be related to the size of the pore or the diameter of the pore using some conceptual equations. Now, we'll point out that this is a conceptual relationship and there's some problems with it, but the basic idea here is that if we use a series of different pressures, we could push mercury into different size pores. So under low pressure, we may push it into the pores here, the big pores, which are shown here by red. This is the large pore that's now being filled with mercury. If we put a little bit more pressure onto the system, we start to see these green pores being filled in. All right, so smaller diameter pores, right, which would correspond on our diagram to the green portion of the curve. And if we go one step further, we start to see us filling in all the smaller pores, which is really the blue pores that are being filled in. And over on our diagram, this is the blue portion of the curve, or the pores that are being infiltrated. All right. What I will say here is that this is a fairly straightforward technique. It gives us information about that relates the pore diameter. All right, so we have large pores to smaller pores. The smaller pores here are shown on the right-hand side of our diagram. Sometimes you will see these graphs flipped around. So we have large pores on the left-hand side. We have smaller pores on our right-hand side. We have the volume on the y-axis. And what you will see is as hydration increases, right, as we go from 28 days to 90 days or 365 days, you'll see the volume of the pores decrease, and we'll tend to see smaller diameter pores. So conceptually, this makes sense with what we saw earlier in the lecture. We saw earlier in the lecture that due to hydration, the pore space was going to start filling in. We saw that over time, due to hydration, the pores were going to become smaller, and this is something that we can pick up with mercury intrusion porosimetry. Now, while mercury intrusion porosimetry can tell us some of the information, it may not necessarily represent all of the pore size distributions that are out there, right? And there are two reasons why, right? One of the things that I will point out is if you actually look at the size scale, mercury intrusion porosimetry tends to miss some of the very, very big entrapped air or air voids that are in the system. It doesn't account for those because it basically doesn't have the resolution to do that. The other thing that you will hear about is something called the ink bottle effect. And inside of the paste, the basic idea is that many of these pores will look a little bit like what I've drawn here on top of this aggregate, where we've got solid material, which is shown here, and I've tried to color that in. We have the pore, which tends to have a large volume, but there is going to be a relatively small neck that mercury is going to be needed to be pushed through. And the basic problem here is while we would be measuring the pore is relatively large, we wouldn't measure it until we've gotten to a high enough pressure to push the mercury through that bottleneck. All right, so sometimes you'll be hearing this referred to as the ink bottle effect, the basic idea that we may not measure all of the big pores until we've reached a certain critical threshold, typically referred to as the breakthrough threshold, to really push the mercury in through the system. There are many other techniques that we'll talk about. I'm not going to go through all of these. All right, there are ways that you can absorb gases onto the surfaces of the particles. We will talk later on in the semester about using electrical properties to get an indication of what the microstructure looks like. We can use NMR. We can replace the water in the system by different types of fluids. All of these are different ways that we can probe the microstructure. They all try to tell us something about different aspects of the porosity, but all of them are somewhat incomplete. And this has led to a lot of debate historically about what the structure of these pastes actually looks like. You'll remember that Powers had his own conceptual model, and there are several other conceptual models that are out there. The model that I've shown here is a conceptual model by Feldman and Serrata, and Feldman and Serrata have taken Powers' ideas and they've taken them a little bit of a step forward, and what they've said is, yes, there are capillary voids, and these capillary voids are pointed to here by this dark black colored arrow. These are the large open spaces, but they also start to try to describe what some of the other water is that's in the system. They say in addition to having water inside of these capillary voids, there is water that's going to be held preferentially along the surfaces of the solids, along the solid surfaces. So what they're saying here is that you could get 4, 5, 6 layers of water molecules that tend to preferentially bond along the surface of the water. And those water molecules are going to be harder to be given up as the system dries. Right? There will be water that's chemically combined that goes into the hydrated products that you'll never get back. And you will also see that they will talk about water that fills in a very fine way, layers in between the sheets of the calcium silicate hydrate. And this is water that's not lost on normal drying unless we get to very, very severe drying, like something below like 11% relative humidity, or we really start to dry the overall system out. Right, so you could think of this essentially as water that's really tightly bound on surfaces, water that's bound on an open surface, and water that exists in a very, very large capillary. Right. In the remaining part here, what I'd like to do is I'd like to take a little bit of time to look at some of the individual components, look at what some of these components look like before we go on to our next lecture, which will be actually going back to Powers' model and doing some of these numerical calculations. All right, as we mentioned before, cement is going to be the brightest component that we're going to look at, and it's shown here with these orange arrows pointing to the unhydrated cement particles. Right? Unhydrated cement is not necessarily a bad thing. It's going to essentially just be a strong, high-priced aggregate. All right, it's an aggregate that's gone through the kiln. All right, it's going to be very dense, which is why it gets that white color. All right, and the goal of concrete is not necessarily to complete the hydration of the cement. It's really to develop a strong microstructure. So having unhydrated cement is not necessarily a bad thing. Right? The second thing that we would look at is our calcium silicate hydrate, and our calcium silicate hydrate can be seen here as these things that look a little bit like rose petals. These are going to be relatively short, amorphous types of structures that are forming, and they're essentially going to be the calcium silicate hydrate that's holding the overall system together. Right? If we look at this, this is going to make up about 50 to 67% of the overall solids volume. Right? It's going to be poorly crystalline. It's going to be relatively amorphous. And we're going to have calcium to silica ratios of about 1.5 to 2 or so. And this is going to be the structure of our calcium silicate hydrate. So as we see on the bottom, you can see this sort of leaf-like structure of the calcium silicate hydrate as it's forming in these layered sheets. Right. As we mentioned before, this calcium silicate hydrate is going to have different names. Some people are going to refer to two different types of products. You'll hear inner product or phenograin essentially being used to describe that dense calcium silicate hydrate that surrounds the cement. You will hear outer product or ground mass being sort of that loose. I talked about it being a mushy or open type of CSH that was really between the cement particles, right? And this is really where the pore solution started out and where the C3S and C2S have been converting in the solution, in situ. The other thing that we will see in the system, we will see these calcium hydroxide grains that are growing. These will be about 20% of most of the systems. These are our calcium hydroxide. If they grow in open space, they will tend to be these hexagonal plates. However, you can also see them when they grow in a confined space. They'll take on a little bit of a different shape. They're layered types of structures, but they will become soluble later on, and this can have an adverse effect on durability. So if water comes into the system, that lime will go back into the solution, and you'll see something that looked solid at one age going back into solution, being transported or being moved through that permeable network, and either leaving the system and going outside the concrete or reforming somewhere else in the overall concrete system. So one of the things that we're going to talk about is how we can reduce the amount of calcium hydroxide through the use of some supplementary materials. As I mentioned before, you will see calcium hydroxide preferentially forming along the surfaces. Right? During the hydration product, it takes less energy for the calcium hydroxide to begin to grow at a surface. So you can see cases where the calcium hydroxide will grow at the surface of an air bubble. You will also see cases where the calcium hydroxide will start to grow at the surface of an aggregate. And this is simply because it takes less energy for it to begin growing off the surface of another material. Right. As was mentioned a little bit earlier, the interfacial transition zone has been something that's between the aggregate particles and the cement paste. So what you can see here is that there is maybe a little bit of a different region of the material between the aggregate and the cement paste. And people have said, well, in order to properly model the system, we should consider this as being sort of a paste phase, an interfacial phase, and an aggregate phase if we consider this as being a three-phase system. And I will say that this is an area where there's actually quite a bit of debate, all right, because most people sort of assume that this is a relatively small region around the sand particles or the aggregate particles. And the reason for this region is for two parts. One, the calcium hydroxide is going to preferentially form there during the hydration process, so it's going to have a lot more calcium hydroxide than what's throughout the rest of the system. In addition, the cement particles can't pack as tightly simply just because there's not enough space for them, so there will tend to be a little bit more porosity. All right. What's been reported in literature is that the structure is progressively more porous as you get toward the surface of the aggregate. So here you can see some pictures again to show this. These are taken from some of the work of Paul Stutzman at NIST. What you can actually see in the lower picture is we've got the aggregate on the inside. We now have this porous region that we may refer to as our interfacial transition zone. And then we have sort of a more solid paste region that we can see a little bit further away from the aggregate. So the region I've circled here is our ITZ. So we've got our aggregate, the interfacial transition zone, and then our overall paste region, giving us our three-phase system. Other people, such as Sid Diamond, have shown that this region tends to go away over time and is not as significant when we start to look at real concrete systems. And one of the reasons that this controversy has really come up is because a lot of times people will look and trying to investigate this interfacial transition zone, they've made very small components where they'll take a single aggregate and they'll stick it next to a cement paste. And the belief there is the microstructure is very different than what you would have in a system with the aggregates actually being mixed in with the cement paste and hydrating in a conventional type of concrete. The other argument that's made that the interfacial transition zone may not be as important as a lot of people say is because it's a spatial distribution. And if you actually look around the aggregate on all sides, you'll see regions where this is actually fairly dense, and you'll see other regions where it's fairly open. All right, so in order to sort of summarize where we're at today, The pore structure, we're really talking about what is and what isn't there. We're really talking about the pore space. We saw as the water to cement ratio decreases, the porosity decreases. We saw as the specimen ages, the porosity decreases as well.